Tonight we are so grateful to have Valerie Higgins. She's a lab archivist and historian in the Information Resources Department at the Fermi National Accelerator Laboratory, also known as Fermilab. And if any of you are like me, you know Fermilab is nearby, but you just don't know much about it. I've been dying to go for a tour, so excited to learn more about Fermilab. Thank you so much for coming tonight, Valerie, and I'll hand it over to you. Thank you.
Well, thank you so much, and thanks for having me, and thank you everyone for being here tonight. I hope you'll enjoy what you'll learn today. So my name's Valerie Higgins. I've been Fermilab's archivist and historian since 2012, and I'm going to give you a basic overview of the lab's history, covering its main organizational and scientific milestones. So let me get my PowerPoint started for you. Okay, and I will, so I can see the Q&A up top, so I will try to keep an eye on that during the presentation. So if you had been at the site that would become Fermilab a little over 50 years ago, you would have seen something like this. This was footage that was filmed around that time. So you would have seen farmhouses, barns, and fields. So in this talk, I'm going to tell you how we got from this to today. So what is Fermilab? Well, Fermilab is America's particle physics and accelerator laboratory. The lab uses complex, powerful machines called accelerators to study particles of matter, particles which are the smallest components of matter. Accelerators use magnets to create beams of very fast moving particles that can then be used in experiments. The lab tries to answer questions like, what are we made of? How did the universe begin? And what secrets do the smallest, most elemental particles of matter hold? And how can they help us understand the intricacies of space and time? So organizationally, Fermilab is part of the US Department of Energy, the DOE. The lab has over 1,700 employees, including scientists and engineers from all around the world, as well as many users from around the world who use the lab's facilities to perform experiments. And the lab collaborates with more than 20 different countries on physics experiments based in the US and elsewhere. Physically, Fermilab is a 6,800-acre site in Batavia, Illinois. This is an aerial view of the lab. One of the things I want to point out in this is you can see that circle in the middle. That is the main ring in the Tevatron. You'll hear more about those later in the presentation. So physicists had been discussing the need for a new accelerator in the US well before the lab was built in 1967. In 1963, a panel of scientists led by a scientist named Norman F. Ramsey recommended that the United States build a particle accelerator with an energy of 200 GeV. So you'll hear me say 200 GeV a few times during this presentation. It means 200 giga electron volts. And it's basically just a measure of energy. It's a measure of the power of the accelerator. In June of 1963, there was a meeting of physicists at Brookhaven in New York, and a prominent physicist named Leon Lederman proposed that what the US needed was what he called a truly national laboratory. Now, what he meant by this was he was commenting on the fact that most of all the particle accelerators that existed in the US at this time were associated with other institutions, with existing institutions. And so the people that worked at those institutions had, preferential access to the accelerators. So what the idea behind the truly national laboratory was that any scientist, no matter what institution they were affiliated with, would be able to propose experiments to use the accelerators at this envisioned truly national laboratory. The next sort of phase in the development of the lab was in June of 1965. The Lawrence Radiation Laboratory in Berkeley, California, produced a detailed plan for a possible 200 GeV accelerator. Now, this was not the final plan that was used for the lab, but it was another step in its development. In November of 1965, the University's Research Association held its first meeting. The University's Research Association, or URA, was a consortium of research universities that was created to manage the lab. So now we have a plan for the lab, like a vision of what it should be, a more detailed plan of how it could possibly be built. We have an organization to manage it. The next step was to choose a site for this lab. So the Atomic Energy Commission, which was the predecessor to today's Department of Energy, they held a nationwide site competition, and there were many different entries of places that were competing to host this lab. But in the end, on December 7th, 1966, they selected Weston, Illinois as the site for the new accelerator. So when Weston was chosen, it had a population of about 400 people. Here you can see an aerial view of Weston shortly after the lab started to move in there. You can see there's lots of little houses in this little town, and the lab has actually preserved many of those little houses. When the lab first moved onto the site, these were the existing buildings. So those buildings you see were the first office and lab space for the laboratory. In addition to preserving those little houses, there were also, this was a 6,800 acre site, so beyond the town of Weston, there were also many farms with farmhouses and barns, and many of those were also preserved by the lab. Many of the farmhouses were moved from their existing sites to that town of Weston, which is now called the Fermilab Village, and many of these houses still exist, and they still provide housing for visitors. So the next step was to select a director for the laboratory. The Atomic Energy Commission chose Robert Wilson in February of 1967, and he would be the lab's director until 1978. And I really can't overstate Wilson's importance as an influence in the direction that the lab took and how the lab formed. When he was selected, he was director for the Laboratory for Nuclear Studies at Cornell University. And one of his first connections with this project was actually when that Berkeley design study came out. He was very critical of it. He felt that it was possible to build a more powerful machine for less money than what that Berkeley design was proposing. So when he was selected to be the director of the lab. His background was interesting. He was born in Frontier, Wyoming in 1914. He spent a lot of time growing up on his family's cattle ranch, and he was a skilled horseman. He was also known for being the youngest group leader on the Manhattan Project. And as a hobby, he was also an avid sculptor. And you'll hear a little bit more about that later and how that shaped some of his approach to things. So in early 1967, the Weston site the lab was ready to begin operations, but the Weston site was not yet ready. The state of Illinois was still preparing it for the lab. So the lab wanted to get started, so they rented offices on the 10th floor of a building in Oak Brook that was partway between O'Hare and the Weston site. And you can see that building pictured to the right here. You might recognize it. If you've driven on I-88, you've probably driven past it. There's now two buildings that look very similar. At the time, there was just the one. So the lab's first offices were actually on the 10th floor of that building. And on June 15th, 1967, about 18 people arrived for work at the NAL offices at Oak Brook, marking the start of the lab. You'll hear me say NAL a few times at the beginning. That stands for National Accelerator Laboratory, which was the original name of the lab. And there you can see Robert Wilson and Ned Goldwasser, the first deputy director. So the first task that the lab employees had to accomplish was they needed to create a design report that would lay out a plan for this new accelerator they were going to build. So that occupied them for the rest of 1967. And they completed that design report in January of 1968. And here you can see the cover of that design report. Later that year, in the late summer and early fall, the lab began and finished moving from those Brook offices to the Weston site. Here you can see the flag raising ceremony on September 24th, 1968, in front of what was the director's first office. So you can see how they used those little houses in Weston as the first offices. On December 1st, 1968, a very snowy day, marked the beginning of the construction of the accelerator at Fermilab. This was at the groundbreaking for what we call the Linac. Linac basically is a way of saying the linear accelerator, and this marked the start of construction at the lab. The Linac was the first in this chain of accelerators that the lab was building. So you can see, despite the snowy weather, many people from the lab and the community were present at this groundbreaking. You can see they had a pretty good turnout. In a moment, you'll see Robert Wilson, the first director, addressing the crowd. And then you'll see him and Glenn Seaborg, who was chair of the Atomic Energy Commission, using this shovel to turn the first shovelful of dirt, marking the start of construction at the lab. And we actually have that shovel in the archives. And sometimes when I'm giving this talk at Fermilab in person, I can show the shovel, but we still have that. So here's just a couple photos from that day again. So the next major milestone for the lab was the groundbreaking and construction of the main ring. You can see they had slightly better weather for this groundbreaking on October 3rd, 1969, a little bit of a safer time to have a groundbreaking in terms of weather than December. But I like this photo of the groundbreaking quite a bit because you can see in the center, the man with his hand raised, that's Robert Wilson, the lab director, and you can't really see it in the photo because it's too small, but he's actually holding up a worm that he's found as they've started digging to break ground on this main ring. So the main ring was that large circle that I showed you before on that aerial view of the lab. And here you can see it starting to take shape on the fields. The main ring is an underground tunnel about 4 miles around that was built to house the main ring accelerator. So the main ring accelerator consisted of 1,014 magnets, and it was used to accelerate particles called protons to very high speeds. And the scientists could then use these fast-moving energetic particles to perform their experiments. So construction on the main ring continued until April 16th, 1971, when the final magnet was put into place. These are just a few more images of the construction of the main ring, and I like to show especially the one on the right because you can see there's some people standing in the mouth of the tunnel, and it kind of gives you a sense of the scale. So the main ring was designed to reach an energy of 200 GeV, and it achieved that design energy on March 1st, 1972. You can see celebrations of that event in the main control room here, and then also here in these videos that were taken on that day. So part of the reason for the celebration was that not only did the main ring achieve this design energy of 200 GeV that it had been built to do, but it was also completed ahead of schedule and under budget. So it was really a big achievement. And there you can see Robert Wilson's excitement at achieving that. And another part of this achievement was that 200 GeV was only the beginning for the main ring. It quickly surpassed its original design energy, achieving 300 GeV in July of that year. And in 1976, it would reach 500 GeV. Wilson ultimately won the National Medal of Science in 1973 for his work on the main ring. And I want to wrap up talking about this day with one of my favorite images from that day, which is this monitor. And you can see the last line says 200 GeV, hip hip hooray. So they were all very excited to reach that. So in February 1972, which was a little bit before that design energy was achieved, the lab's experimental program began. And it began when experiment E36 began taking data. E36 is a very interesting experiment. It's noteworthy not just for being the lab's first experiment to take data, but it's also, it was a collaboration between US scientists and Soviet scientists during the Cold War. And I find this interesting because I think it really shows how important international collaboration has been at the lab since the very beginning. Many of our experiments today are larger and are very international, but that really goes back even to this very first experiment was this international collaboration. So once the accelerator was up and running, it could be used to send beams of particles to experiments. At the time, there were three main experimental areas: the meson area, neutrino area, and proton area. And interestingly, each of those areas has a distinctive structure that we kind of associate with it. As you can see, these are not your standard, they're not like standard boxy buildings. There's clearly been a lot of attention paid to the design of these buildings, and that really traces back to Robert Wilson's influence. One of the things we have in the lab archives is Robert Wilson's drafts for his memoirs, and in those he states that one of his conditions for taking the job at the lab was that within the constraints of the budget that he had for building, he wanted pretty free reign with the architecture, and it was very important to him that the lab have attractive, inspiring buildings, because he wanted the buildings to reflect the importance and the uniqueness of what was going on at Fermilab, and two, he knew that they'd be trying to draw the best scientists in the world to this lab, and so he wanted to create a site that would be beautiful and inspiring to the people that worked there and visited there. Wilson, as I mentioned before, was himself a sculptor. So another way he influenced the appearance of the site is many of his own sculptures are on display at the site. These are two of our most well-known sculptures that are near Wilson Hall. And then if there's any sculpture of his that you're familiar with, it's likely this one, Broken Symmetry, which stands over our main entrance. Another thing that came out of this importance that the appearance of the lab, that the aesthetics of the lab had for him, was Angela Gonzalez. Angela Gonzalez was the lab artist, and she was employee number 11. And so I think that really tells you just how important this was to Wilson, that he was starting this new lab, and the 11th person he hired was an artist to be the lab artist. So Angela Gonzalez chose the lab's bold color scheme of blues, oranges, and reds. She also created our iconic logo, which she created by combining these sort of designs of two of the magnets that were used in the main ring accelerator. And you can see in this image how she has played around with the shapes of those magnets and has eventually come up with that number 18, which is our logo still today. She also designed very striking posters and publication covers for the lab. These are some of the things that I really, have loved about working in the Fermilab archives, is seeing, her artwork that she created for some of these things. It's really beautiful. So in addition to bringing an aesthetic sensibility to the lab, Robert Wilson was also very interested in the natural environment of the lab and in both preserving and restoring it. So this slide shows some of the things that he did with trees at the lab. So on the left is a picture from the lab's first Arbor Day on May 2nd, 1969. Now, if you'll recall, they just had moved on to this site in the late summer and early fall of 1968. They had just broken ground on the accelerator that December. So that very next spring, they're holding this big Arbor Day to plant all these trees. So again, I think it just shows what a high priority this was for Wilson and others at the lab. And on the right, you can see a clipping from one of the lab newsletters where Wilson urges people to please not unnecessarily cut down trees. And so I think, again, it just shows how important this was to Wilson. Of course, I can't talk about the history of Fermilab without talking about the bison. So Wilson brought the first bison to the lab site in late 1969. It started with 6 animals. Most of them came from Colorado. One of them came from Wilson's home state of Wyoming. And then about a year later, they incorporated a larger group from Illinois to the herd. And the bison that we have today, while they do, of course, bring in different bison from time to time to keep the genetics of the herd diverse, the bison that we have today still can trace their ancestry back to these original bison. And so this is our herd, the piece of the herd as it was in 2016. Another interesting detail, a few years ago, they did some genetic testing on these bison, and apparently I learned this from when they did this. Many bison that exist today actually have some cattle genes mixed in because they've been interbred with cattle. But the bison that Fermilab has are actually 100% pure bison. So that's also kind of a special thing. So in addition to preserving trees and bringing the bison back, Wilson also, it was under Wilson that the prairie restoration effort started. So that started in May of 1974. It was one of the earliest efforts of its kind. It began with restoring the tallgrass prairie inside that, the circle of that main ring accelerator, but it eventually expanded far beyond that. And by the late 1980s, it was one of the largest restored prairies in the world. So with things like the bison and the prairie, there was a lot of frontier imagery in the early days of the lab, and that wasn't a coincidence. That was something that, Wilson had an enthusiasm for the idea of the frontier, because in part he and others at that time saw science as the new frontier. And so they deliberately incorporated a lot of frontier imagery in the early days of the lab, and we still continue some of that today with things like the Frontier Pub at Fermilab. So construction of Wilson Hall, which was originally called just the Central Laboratory Building, began in 1971. This is another iconic part of the lab that Wilson had a big influence on. It was designed by architect Alan Ryder, but Wilson definitely had an impact on it. When he was describing, what he wanted, two of the things that he drew on were the Ford Foundation building in New York. He very much liked the large atrium inside that building. And if you've ever been inside Wilson Hall at Fermilab, you'll know there's an atrium that goes from the first floor all the way up to the top. So that was one of his inspirations. One of his other inspirations was cathedrals in France. When he had visited cathedrals in France, he had been very struck by the way, they really soared over the landscape and how you would see them from a distance. And then as you approached closer, sometimes they'd be obscured by trees or other things, and then you'd get closer and, you'd see them again, and then they'd, be obscured, but then you'd eventually reach them and it would be this big, this big soaring building. And he wrote that he wanted to have a similar effect at Fermilab. And he also knew that the site was very spread out, very large, and he felt it was important to have a high-rise building that would really bring people together, and that would also be a sort of focal point for the lab site. And so that's what he was hoping to achieve with this building. And so it was completed in 1973. You can see it there. And shortly after it was completed, the lab's dedication ceremony was held in front of it on May 11th, 1974. And it was at this point that NAL became Fermi National Accelerator Laboratory. And very quickly, people started calling it Fermilab. That was also a decision of Wilson. He felt that Fermi National Accelerator Laboratory was unwieldy, and so he championed calling it Fermilab. So it was named in honor of Enrico Fermi, who was a world-renowned experimental and theoretical physicist who had left Italy for the US and just before World War II. And he had been played a key role in the Manhattan Project, and then he had spent much of his career at the University of Chicago, which was of course not far from Fermilab. And so it was felt that naming this new lab in honor of Enrico Fermi would be fitting. Now, Enrico Fermi had passed away well before the lab was established, but Laura Fermi, Enrico Fermi's widow, did come and speak at this dedication event. So one of the lab's first major scientific milestones was the discovery of the bottom quark by experiment E288 in 1977. Physicists had theorized that this particle existed, but they had to perform this experiment to actually find that it did exist and to discover the properties of that particle. So here you can see the team that made that discovery. On the right, you can see Leon Lederman is the man in the back who's seated on the desk. You might recall I mentioned him before, that he was the one that had proposed that idea of the truly national laboratory. And he would eventually go on to be the lab's second director. And here he was the leader of this experiment as well. The other thing I want to draw your attention to that you also could see in that when I showed you the photograph of experiment E36 is just look at sort of the size of the collaboration. Like, you know, you're looking at a dozen people, somewhere around that. And so that gives you a sense of what the size of the experiments were at that time. And you'll see how, as the lab's history unfolds, how that will change. So this is a chart called the standard model. You'll see this a couple of times during my talk, and this is basically it's a chart that physicists use to represent the most fundamental particles and forces in the universe. The way I sometimes think of it is it's like if you're familiar with the periodic table of the elements, it's a little bit like that, except these are much more fundamental particles and forces, much more fundamental things. So this is the symbol that represents the bottom quark. So this is that particle that Fermilab discovered in 1977, this part of the standard model. So the next phase in the lab's history was the energy doubler, or as it would later become to be known, the Tevatron. This is a drawing of this planned energy doubler by Angela Gonzalez, that artist I mentioned earlier. So as early as the summer of 1967, Wilson had talked to his staff about the possibility of one day increasing the energy of the accelerator by using a technology called superconducting magnets. So superconducting magnets are magnets that are kept very cold, which lets them run more efficiently and thus produce more powerful accelerators. And so when the lab was building the main ring, they knew there was this possibility that they might eventually, you know, that they would eventually want to upgrade it in this way. And so they deliberately left enough space in the tunnel to allow that to happen in the future. So there were tentative talks about it as early as summer of 1967, but they began formal work on this plan the day after March 1st, 1972, because March 1st, 1972 was when they achieved that design energy of 200 GeV. So as soon as they achieved that, then they began official work on upgrading the accelerator the day after they, you know, achieved their initial goal. And then in 1976, the lab held its first meetings about the possibility of adding a collider to the accelerator. And so what that means is that this collider would have you'd have a beam of protons, which is what the main ring was working with at the time. You'd have a beam of antiprotons, and then you'd have like both these beams of the beam of protons, the beam of these antimatter particles called antiprotons, and you would then collide them together, and it would produce much more energetic interactions for the physicists to study. It would let them study things more deeply than they could without the collisions. So while this project was underway, Wilson decided to leave the lab. And so he submitted his resignation on February 9th of 1978. And the central laboratory building was named in his honor as Wilson Hall on September 18th, 1980. Fortunately, the lab was left in the very capable hands of Leon Lederman. I've already mentioned him several times in connection with the Truly National Laboratory as the leader of E288 that discovered the bottom quark. So he had a lot of ties to Fermilab. He was also known for his work with neutrinos. In the early 1960s, he and his colleagues had studied neutrinos and proved that there was more than one type of neutrino, which you'll hear a bit more about later. And that work would eventually earn him the Nobel Prize in 1988. He, in addition to being a great scientist, he also had an excellent sense of humor. On the right, you can see a photo of, on the left is Robert, these shirts that they're wearing are Lederman's doing. And on the left, you can see the first lab director, Robert Wilson, wearing a shirt that says founder. And on the right, you can see Lederman has put himself in a shirt that says flounder. And that's sort of typical of his, his sort of humor. So in addition to being a skilled scientist and administrator, Lederman was also very passionate about science education. And a lot of the lab's really great educational and outreach programs that we have, they really trace back to Lederman for the most part. So one of the programs that he was one of the starters of is this Saturday morning physics, which it still goes on at the lab today. It began in 1980, and you can see here Lederman teaching one of the Saturday morning physics classes from that first year. And so Saturday morning physics is a program that brings high school students from nearby to the lab to attend these Saturday morning lectures by Fermilab physicists. Lederman also started other educational programs at the lab. He's also known for being one of the founders of IMSA, the Illinois Math and Science Academy in Aurora, which you may have heard of as a very well-regarded school. So in recognition of all his work with science education, the lab's Lederman Science Education Center was named in his honor in 1992. So under Lederman's leadership, work continued on the Tevatron. The Department of Energy authorized its construction on July 5th, 1979. And it was the world's first superconducting accelerator. And in its final form, it was a superconducting accelerator and a proton-antiproton collider, as I mentioned before. And so it used the old main ring to supply the beam of protons. And then the lab also built this antiproton source to supply the antiprotons. It consisted of about 1,000 additional magnets installed in that main ring tunnel. The Tevatron is actually what you see below. You see these two rows of magnets in the tunnel. The Tevatron is the red one below. And the Tevatron collider was dedicated on October 11th, 1985, and the first collisions were observed just a few days later on October 13th. The Tevatron was a very significant scientific and technical achievement, and Rich Orr, Dick Lundy, Helen Edwards, and Alvin Tallestrup received the 1989 National Medal of Technology for their work on the Tevatron. You can see them here. So these collisions that I've mentioned, those happened at two locations, and there were detectors at each of these locations, these experiments CDF and DZero. So you can see where those were located. And these beams of particles, they moved very, very fast, close to the speed of light, to the point that they crossed each other at these locations of these detectors 1.7 million times every second. So it gives you a sense of just how, how fast these particles were moving. And so these two detectors use different technologies to analyze these events. So they complemented one another. Here you can see the CDF detector and the DZero detector. You can also get a sense of their scale, seeing, both those photos have people on the, standing right near the base of the detector. And even those photos, don't really do it justice. I've had the chance to stand near the, parts of the DZero detector, and it's really, it's massive. And not only are the detectors large, but the collaborations that were, made up the people in the experiment, they were very large as well. At their height, they each had more than 500 people. So here you can see partial collaboration photos because these aren't even all the members, but compare what you're seeing here to what you saw with E36 and E288. You can see the size of the experiments has just grown enormously as the lab tackles, more difficult experiments, more difficult questions. So Leon Lederman won the Nobel Prize in 1988 for the work he had done back in the early 60s. And shortly after he won the Nobel Prize, he chose to leave his position as director of the lab. So he was replaced by John Peoples, who became director in 1989 and served until 1999. John Peoples also had many close ties with the lab when he became director. He had started the lab in 1971. He'd held many important positions. He'd played a key role in the Tevatron. So he definitely had a lot of strong ties to the lab when he became director. One of the lab's main accomplishments that the Tevatron enabled while John Peoples was director was the discovery of the top quark. So like the bottom quark, the top quark had been predicted, but scientists had to build these massive experiments of CDF and DZero in order to actually find it and find what all its properties were. You can see here the day that the discovery was announced on March 2nd, 1995. That's Ramsey Auditorium at Fermilab's Wilson Hall, and you can see it's packed as everyone listens to this announcement. And that's a representation of the particle collisions that produce the top quark. So here's that standard model again, and now you can see Fermilab has added the discovery of the top quark to its accomplishments. So just as the seeds of the Tevatron were being discussed before construction on the main ring even began, Fermilab was already thinking about how to improve the Tevatron in the mid-1980s. And so the plan that they developed was that initially the old main ring was used to supply the Tevatron with protons, but the lab wanted to build a new proton accelerator called the main injector to replace the main ring. And that would allow the Tevatron then to be more powerful because you'd have this more powerful accelerator earlier in that chain of accelerators. So the groundbreaking for the main injector happened on March 22nd, 1993. And it was completed in 1999. And the main injector is that oval-shaped accelerator that you can see to the left of the main ring. And so that accelerator is still used today. That is still the lab's main flagship accelerator. And it's about 2 miles around. So up until this point, I've been focusing mainly on Fermilab's work with experiments using particle accelerators, but Fermilab is also heavily involved in astrophysics, which uses observations of the cosmos to study fundamental particles and forces. And so some of that began with the Theoretical Astrophysics Group, which was formed at Fermilab in 1983. At the time, particle astrophysics was a very young field, and so Fermilab has really played an important role in shaping this field. And one of Fermilab's first astrophysics experiments was the Sloan Digital Sky Survey. You can see the collaboration for that here in 1993. And so that used a telescope based in New Mexico to create detailed maps of the universe. And it received first light, which means it started making its first observations on May 9th, 1998. And John Peoples was the director of Sloan Digital Sky Survey from 1998 to 2003. Another little thing I want to mention while we're in this time period of the early 90s is the development of the web. So that's something that came out of CERN, a particle physics laboratory in Europe, but Fermilab became involved very early. Fermilab had one of the first 3 websites in the United States, and here you can see the lab's very first website, which was from 1992, the lab's computing division website. So you can see, what a very early website looked like, and if you go and look at Fermilab's website today, it will of course look very, very different. So Mike Witherell became the lab's director in 1999, and he served as director until 2005. So there are big changes on the horizon at the time that he became director, because CERN, that European particle physics laboratory I mentioned earlier, it's located near Geneva, Switzerland. It was building the Large Hadron Collider. The construction on that had started in 1998, and it was set to become the world's most powerful accelerator. It would be a superconducting proton-proton collider. Fermilab was actually very involved in this effort. Fermilab scientists helped design and build some of the accelerator's magnets at Fermilab. But having the LHC on the horizon meant that Fermilab would need to look at some different directions it could take, because many of the experimenters who wanted to use the kinds of particle collisions that the Tevatron could produce would want to use the LHC for their research. So Fermilab prepared to shift some of its focus more towards studying neutrinos. Neutrinos are very unusual particles. There's about 100 trillion of them that pass through you every second, but you don't know because they very, very rarely interact. And because they so rarely interact, they're very elusive, they're very difficult to study. And so to study them, you have to produce a lot of them, because when you have a lot of them, you have more of a chance that you're going to actually get an interaction from some of them. So they're the most abundant matter particle in the universe, but we know relatively little about them. So as Fermilab prepared to increase its focus on neutrinos, they built the NUMI beam, which NUMI stands for neutrinos at the main injector, and it uses the main injector proton beam to produce the world's most intense high energy beam of neutrinos. So work on that began in 2000 and it was completed in 2005. And this really set the stage for Fermilab to expand its work in neutrino experiments. Now, of course, Fermilab had been doing research with neutrinos since the early days of the lab. In fact, the very first experiment proposal submitted to the lab was for a neutrino experiment, and there was that neutrino area in the fixed target areas of the early lab, but this really represented a shift to an increased focus on neutrinos. So the lab's experiment Minos used the NUMI beam, and it was the lab's first long baseline neutrino experiment. So what this means is a long baseline neutrino experiment is an experiment where you produce a beam of neutrinos at Fermilab, this very intense beam of neutrinos, and then you send it a very long distance straight through the Earth, no tunnel needed, because since the neutrinos interact so rarely, you can just send them straight through the Earth and they're not bothered. And so what you do is you have a detector, a near detector that's at the lab. And so you create this beam, you look at the beam with your near detector, then you send the beam this long distance away, and you have a far detector, and then you look at the beam again and you see how it's changed. And it has changed because I showed you earlier, there's 3 different types of neutrinos, but one of the things that makes neutrinos so very strange is one type of neutrino can change into the other types of neutrinos. And that's something that Fermilab scientists are still trying to understand more about what that means and how that happens. So Minos was an experiment that stood for main injector neutrino oscillation search, because that change between the different types of neutrinos is called oscillation. So the near detector was at Fermilab. The far detector was all the way in the Sudan mine in Minnesota, about 450 miles away. And here you can see that far detector hall under construction. So groundbreaking for the detector hall happened in 1999. The experiment started running in 2005 and it ran until 2016. I like this image of the detector hall because on the right you can see there's a mural painted on the cavern, the wall of this detector hall. And so this is just another example of how Fermilab has continued this tradition of bringing art into science. So during this time, Fermilab made another milestone discovery when the donut experiment became the first experiment to directly observe the tau neutrino. And that was announced on July 21st, 2000. And so here's that standard model again, and now here is the tau neutrino that the Fermilab experiment donut was the first to directly observe. Piero Done became the lab's director in 2005, and he was director until 2013. During his time as director, the LHC came online. That was completed in 2008. To give you a sense of the scale of this, the Tevatron is a little over 1,000 magnets, about 4 miles around. The The Large Hadron Collider is 10,000 magnets, about 10,000 magnets and about 17 miles around. So, you know, significantly larger. And one of the major experiments at the LHC is the CMS detector. And here you can see that detector. So CMS is kind of like CDF and DZero, but in the sense that it's, you know, a detector observing these particle collisions, but it's much larger. You can see physically it's much larger. There you can see if you look carefully down at the bottom of the photo, there's a person standing below there. A few years ago, I had the chance to actually travel to CERN and to see this detector in person. And it's really stunning. It's enormous. And it's incredible to see. So in addition to the detector itself being so large, it's also a very large collaboration, where CDF and DZero at their peaks had over 500 people. There's about 2,600 people in CMS. So again, it just gives you a sense of this growing scale. But something to keep in mind with all this, you know, this is a very international effort, and Fermilab was heavily involved in CMS. Fermilab provides support to the more than 600 US-based scientists that work on CMS, and Fermilab helps process data from CMS. And Fermilab also has a remote operations center in Wilson Hall, from which Fermilab scientists can run remote shifts at CMS from Fermilab. So it's really, you know, this field is very international and very intertwined. But shortly after the LHC and CMS were up and running, the Tevatron was shut down, and that happened on September 30th, 2011. And here you can see a photo of Helen Edwards, who had played a key role in the design of the Tevatron, is hitting the switch to turn it off for the last time. Now, you might remember from a few years ago now, on July 4th, 2012, the experiment CMS and Atlas at CERN announced the discovery of the Higgs boson, the particle that's responsible for giving other particles mass. And again, Fermilab scientists played a key role in this discovery. This image is a simulation of one of the collisions observed at CERN. And so here's that standard model again. And there's the Higgs boson, which Fermilab scientists collaborating with other scientists from around the world helped discover. So during this time, the lab's involvement in astrophysics was also continuing. Fermilab started the Dark Energy Survey in 2003. It's an international collaboration, about 400 scientists from about 7 countries. And it uses a camera mounted on a telescope in Chile to survey the sky to investigate the effects of dark energy, which is, we're not able to observe directly, but it makes up most of the universe. And one of the reasons I like talking about the Dark Energy Survey is because it produces such beautiful images like this one that you see here. It took its first pictures in 2012. Our current director, Nigel Lockyer, started in 2013. And in the last few years, Fermilab has continued to focus on neutrino physics. The NOVA experiment represents the first generation of long baseline neutrino projects after MINOS. It also uses the NUMI beam. It's the lab's current flagship neutrino experiment. And here you can see the near detector at Fermilab and the far detector, which is in Ash River, Minnesota. And again, you can see the scale of these detectors, especially that far detector. And those detectors were completed in 2014. Looking to the future, the long baseline neutrino facility and the deep underground neutrino experiment, LBNF and DUNE, are the future flagship projects of the lab. This is another long baseline neutrino experiment. LBNF will be internationally designed, coordinated, and funded. And DUNE will use an upgraded neutrino beam that will be the world's highest intensity neutrino beam. The near detector will once again be at Fermilab, and the far detector will be at Sanford Underground Research Facility all the way in South Dakota, which is about 800 miles away. So, you know, it's an even larger scale experiment. The far detector will be massive. It will be 4 stories high and will occupy an area about the size of a soccer field. And DUNE will help scientists understand things like why there is more matter than antimatter in the universe and other fundamental properties of the universe. So the DUNE collaboration officially formed in 2015. You can see here a photo of some of the members of the collaboration in 2018, and it currently has over 1,000 collaborators from 180 different institutions in more than 30 countries in CERN. So again, this just shows you how the scale of experiments has increased. The DUNE hasn't started yet, and already the collaboration is bigger than the CDF and DZero ever were. So the lab held the groundbreaking for LBNF at the Sanford Underground Research Facility on July 21st, 2017. They actually called it an underground breaking because it's deep in this mine in South Dakota. So the construction is actually happening, a lot of it underground. Another important part of the lab's future is PIP2, which stands for Proton Improvement Plan. This project is going to replace the lab's current linear accelerator, the Linac, with a superconducting Linac. So we're, up until now, we've still been using the same Linac that was built in 1968. When you saw that those, groundbreaking photos, the snowy ones with the shovel and everything, that was that Linac that they were breaking ground on there is the one that the lab has still been using. So it's time for the lab to replace that. And just as upgrading from the main ring to this superconducting Tevatron ushered in a new era at Fermilab, this new superconducting Linac is also going to open up many new doors for scientists. So these improved proton beams that it will help the lab produce will make the DUNE experiment possible. And here you can see what where PIP2 will be on the lab site and what it will look like. Another thing that's unique about it is that while Fermilab has frequently hosted experiments and detectors with strong international involvement, PIP2 is the first accelerator project in the US that will have significant contributions from international partners. So I'm getting towards the end here. So there's so many other things I wish I could talk about at Fermilab. I've talked about some of our biggest experiments, but there's all kinds of other experiments I haven't had a chance to talk about. I'd encourage you to, visit our website, reach out to people at Fermilab. There's lots of resources to learn about what goes on at the lab. But I will wrap it up there so we can have some time for questions.
Thank you so much, Valerie. We learned so much. That was fascinating. If anyone has any questions, you can just put them in the Q&A or the chat at the bottom, and we will take a look at those. I'm guessing is the lab closed right now, or are scientists working remotely or on site?
Oh, yeah. Okay, so scientists are definitely working remotely. The lab is definitely still doing its scientific work, but the lab is closed to the public at the moment, yes.
Yeah, that makes
sense. But there's a lot of great resources. If you visit like our education website, there's all kinds of resources that the lab has online that you can use to learn about the lab, and you can use to learn about particle physics at home.
I was wondering, does Fermilab still employ an artist on site? Because I thought that was very interesting.
Yeah, so we don't actually have an artist. We do still have an art gallery on the site, and that we have changing exhibits featuring all different kinds of artists, and so we have an art gallery curator, and we have a graphic designer. We do have an artist in residence program. So it's different, it's not a lab employee, but we do have this program that artists can apply to be an artist in residence working with the lab.
That's great. I love that you incorporate art with science. It's so interesting. Let's see.
So yeah, so I'm seeing the question in there. So yeah, up until, of course, the closure with the pandemic, bike riding was definitely permitted on the lab site. I saw all the time, people would come on and ride their bikes, and we have the Margaret Pearson Memorial Trail is a trail through the restored prairie. So all of that, all of that exists on the site, and I expect that once, once things are back to normal, that I don't see any reason why those wouldn't reopen again.
And we do have a question, how are experiments chosen?
So that is done by, there's like, it's basically like a committee that consists of not just people at the lab, but also people outside the lab. It's this physics advisory committee and the director. And so it's that group of people that make those decisions. And then I know I took it down, but I probably should have left it up a little bit longer. If anybody wants to have the information, let's see here. I posted my contact information. So if you have any questions later, I'd encourage you to contact me at here. I'll put my email address and my Twitter account and things in the chat.
Thank you. We do have a question. If you could comment on the plans to build a huge accelerator in Texas about 10 years ago. Construction was started, but the plans were scrapped. Yeah,
so that was the superconducting super collider. And so that was planned, I think the planning began maybe early 1980s. Yeah, it was supposed to be built down in Texas. Construction started in either the very late 80s or the very early 90s. A fair bit of construction was done, and then it was canceled in 1993. And so that if the superconducting super collider had been built, that actually would have been a larger and more powerful accelerator than the Large Hadron Collider, and like the Higgs boson that was discovered in 2012 may well have been discovered, in the late 90s or early 2000s. And if you want to know more about the superconducting super collider, the SSC, I'd suggest there's a book called Tunnel Visions that one of the co-authors is actually a former archivist from Fermilab, and that's a very good book about that if you're interested in that.